All right, so again, looking at what we've got here in this little explore, we'll read through this here real quick and then we'll get into the activity. So it says linear, quadratic, and cubic functions belong to a more general class of functions called polynomial functions, which are categorized by their degree, right? We kind of talked about degree some yesterday. Linear functions, right, functions whose graphs are lines, are polynomial functions of degree 1. Quadratic functions are polynomial functions of degree 2. Cubic functions are polynomial functions of degree 3. Okay? In general, a polynomial function of degree n has the standard form, and then there's this mess here, but you get the idea. You know, it starts with x to the n, and it goes down to x to the n minus 1, and so on and so forth. Okay? A polynomial function of degree 4 is called a quartic function. Okay, it's like the word quart, right? When you buy like a quart of milk, right? A quart of milk, or a quarter, right? That's probably even a better explanation than quart. So while a polynomial function of degree 5 is called a quintic function. I'm trying to think of like where you see the word quin in front of it like that, but I don't know. Anyway, after degree 5, polynomial functions are generally referred to by their degree, as in a 6th degree polynomial function. Okay, so you don't really have a name for it after a 5th degree. And really, 4th degree, like a quartic and a quintic, you rarely hear that term used too. But they're there, so I guess this book uses it. So anyway, we're going to use a graphing calculator to graph these polynomial functions. So let's graph f of x equals x. Okay, so... Or if you want, you can just follow along with mine, I guess, too, since this one, we all know what this one looks like, right? It's going to be a line. Ooh, there it is. Okay. What is the domain of this polynomial function? All real numbers. So you can just put a little, well, not a little, capital, R there with the two lines. Okay. What's the range of this polynomial function? All real numbers, same thing. Okay, good. Now, end behavior. Now, this is something, right, we got to be careful with here. So, as x approaches infinity, so as we go further and further to the right, what's the value of f of x going to approach? Positive infinity as well, right? It's going to keep going up and up and up and up. As x goes to negative infinity, so as we go further and further and further left, what's the value of our function going to approach? Negative infinity, because it's going down as we go from left to right. Yeah, that's right, Greg. Okay, that was pretty straightforward. A line with all real numbers for the domain and range, and then end behavior. If x goes to positive infinity, f of x goes to positive infinity, and if x goes to negative infinity, f of x goes to negative infinity as well. All right, let's look at x squared. And this should be a graph that we are familiar with. You maybe can imagine it in your head without even having to see it, but let's take a look at the picture here anyway. Okay, same questions. What's the domain of this function? All real numbers is right. Okay, so I'll just put that right here.
Don't question it, Greg.
Hang on. We asked for the right. Don't question it. No, it's important to question things, right? We can get into trouble if we don't question things. The domain deals with x values, right? So So what's the range though? All real numbers, right? No, because it doesn't go all the way down, right? Yeah, sure, a minimum in this case, yes. And so the range, we can describe it a bunch of different ways, right? We can say y is greater than or equal to 0, right? Or we could use the interval, 0, comma, infinity. That's also acceptable. I'm not going to bother with set notation because it's the same idea as the inequality, just with a little bit more stuff to write. All right, what about the end behavior? As x goes to infinity, so as the x values get bigger and bigger and bigger, what happens to the value of our function? As we go further and further right on the x-axis,
it goes positive.
Positive infinity. Very good. And as x goes to negative infinity, what happens to the value of our function?
It goes positive.
It's also positive. Okay, so different end behavior here, right? In this case, they both go to positive infinity.
What was the
Range,
range?
was either y is greater than or equal to 0 or 0 to infinity, right? Because you can see that the lowest y value is, there you go. The lowest y value is at 0 there. Okay, I need one of those special backlit ones, I think. All right, let's try one more here together, and then I'll have you guys take a look at some of these, okay? So last one here, x cubed. Again, this is one we should be pretty familiar with based on our experiences most recently. Okay, so what's the domain of this?
All real numbers.
All real numbers. What's the range of this? Oh, real numbers again. Yeah, in this case. As x goes to infinity, so as we go further and further to the right here, what happens to the value of our function?
Goes up.
Goes to infinity. And as x approaches negative infinity, as we go further and further left, what happens? Goes down to negative infinity. Okay? So if you would, please go ahead, use your graphing calculators, fill in the rest of those 3 rows there. Okay? F of x equals x to the 4th, x to the 5th, and then x to the 6th. Go ahead and fill the rest of those in. Oh, crikey. Okay, so let's see, we can fix this. If you arrow up, so were you using this in like another class or something
No,
like
it
that?
was, well, my brother.
There you go. So if you just arrow up and hit enter, it'll turn off the plots, but of course now you want the rest of the graph. So you hit zoom 6.
Okay.
Okay, so like the zoom has a bunch of like preset windows in it for you to use, and the standard one is Z6, Z standard, and that takes you right back to like the normal viewing window that you see. Okay. Ooh, interesting. Okay, yeah, so I don't, do you have a friend that uses this in another class, or do you use it or something? So something might have happened here. You just turned on your plot 1. That's for like if you want to plot data, but I'm assuming you probably don't have any data in there. So now if you go to graph it, you should be fine. And you might want to hit zoom 6. Zoom and then the number 6 because to get the standard viewing window to show up again. Okay. I guess I should probably do this too. Let's see here. Okay, so again, use those graphing calculators. Get an idea. x goes to negative infinity, I want to the range of this function. Is it all real numbers? Do you hit every single y value here? No, so what's the range going to be? This one should be all real numbers. I think you maybe got like out of order or something like that. What happened there? That's good. All right, and then we'll get the last one here for you up on here on the board. All right, so here we go. This is what we should have gotten right here. Okay. So you'll notice the domain for all of these. All the domains are all real numbers. The ranges, though, what happens to the ranges? They're not all real numbers. But do you see any like relationship there? For the ranges?
It's the positive.
Okay, what do you mean it's the positive numbers?
The positive numbers. The tiny.
The exponents, right?
The exponents.
Okay, what about the exponents? I think Miranda had something to say. What did you say, Miranda? What about so the even ones, their ranges are the limited ranges, right? That's y is greater than or equal to 0, y is greater than or equal to 0, y is greater than or equal to 0. Very good. Whereas the odd degrees are all real numbers, right? The degree of 3, real numbers. The degree of 5, all real numbers. The degree of, what's the degree of this one again? 1, all real numbers. Okay. Also look at the end behaviors too. They kind of match up in a similar way that Miranda said. If you look at the even ones, 2, 4, and 6, they all both go to positive infinity. If you look at the odd ones, 1, 3, and 5, so like those three, as x goes to positive infinity, fx goes to infinity, and as x goes to negative infinity, fx goes to negative infinity. And there it is, infinity, infinity, negative infinity, negative infinity. Infinity, infinity, negative infinity, negative infinity. Okay? So, we group these things based off of their degree to help us discover their, to know their domain, their range, and also their end behavior. Even degreed polynomials, domains all real numbers, range will be y greater than or equal to 0, and then the end behavior, they'll both go to positive infinity, or they'll both go to negative infinity if we have a negative lead coefficient. Okay? If it's an odd degree polynomial, domain and range will always both be all real numbers, and then the end behavior will be different. They'll disagree. In this case, for a positive x cubed, if x goes to infinity, then f of x goes to infinity, and as x goes to negative infinity, f of x goes to negative infinity. Okay? Over here on the other page, all right, and we're not, if you turn the page there, we're not going to do this. This is just like too much, more than we need to do, I think. But you'll notice here they want to do the similar thing, but now our functions have a negative 1 in front of them. Well, what is that negative 1 going to do to the graph of all these functions? What is a negative 1 in front? What does that do? How does that transform the function? Flips it over the x-axis, right? So, for example, negative x is now going to look like this. Domain will still be all real numbers, the range will still be all real numbers, but the end behavior will flip. It'll go to negative infinity, or the function will go to negative infinity as x goes to infinity, and as x goes to negative infinity, fx will go to positive infinity, so the end behaviors flip. Here for negative x squared, instead of being the u, it'll be like the frown, right? The bell shape or something like that. Like that. And so then the domain will still be all real numbers, but now the range won't be 0 to positive infinity, it'll be negative infinity to 0. And then both of them will point down. And behaviors will go down. And so on and so forth. Okay? That's the idea there. All right? So, and I'll make a nice little chart for us here to help things out. So, in fact, let's just go ahead and go down here and do that. Okay? So down here at the bottom, maybe I'll kind of try and squeeze this in. So we're going to use this space here to help us out. We're going to generalize for the end behavior at least. So we'll just say this is for the end behavior. Okay? And we're going to have a little chart here that I'm going to make. So let's see here. I'm going to do something like this, and then something like this. Okay? So if the degree is odd or even, right? Those are the two things we talked about, but then we also had the lead coefficient that we had to think about as well. Is the lead coefficient positive or is it negative? Okay, positive or negative. So if we have an odd degree and positive lead coefficient, then as x approaches infinity, f of x will also approach infinity. And as x approaches negative infinity, f of x will approach negative infinity. Okay? Think of like a cubic, x cubed, right? X cubed, as you go further to the right, it goes up. As you go further to the left, it goes down. So you can think of like x cubed there. Okay, kind of like that. We'll draw a little picture in there of it. Okay. If we have a negative lead coefficient, this graph will flip, and it's going to look like this. Okay, so as x approaches infinity, f of x will now approach negative infinity, and as x approaches negative infinity, f of x will now approach infinity. So it just flips the infinities there. Okay. Let's see if I can zoom in a little bit better on that. All right. And then for even degree, so think, in this case, think of like the quadratic equation, or quadratic function, right? Looks like the u there. As x approaches infinity, f of x will approach infinity, and as x approaches negative infinity, f of x will still approach infinity. Right? Either direction you go, it's going to go up. But then if you have a negative lead coefficient, that'll make the parabola be upside down. And so then as x approaches infinity, f of x will approach infinity. And as x approaches negative infinity, f of x will approach negative infinity as well. Okay? So those are your four different situations for the end behavior. Four different situations for the end behavior. Okay, so let's turn to page 253, and we'll take a look at then a polynomial whose graph we're going to sketch. Okay, so let's look at page 253, and we're going to look at example 1 here. Okay, so first thing we want to recognize here, okay, our polynomial, it's not in standard form, right? It's not like multiplied out. It is not multiplied out, it's like factored for us already. So, by looking at this, if we were to multiply this out, what would the degree of this polynomial be? If we were to multiply this out, what would the degree be? What's that? What's the highest powered term that we would have? A cubic, right? Or a 3 would be the degree. Exactly right. X times x times x. Those will eventually all get multiplied together, and so we'll have x cubed. Okay? So the degree is 3. So the degree, in other words, is odd. What about the lead coefficient? Positive or negative? How do you know? Took a wild guess. Well, that's true. 50-50, right? Let's think about this. Just like I was saying earlier, if you do x times x times x, we know that we're going to have to do x times x times x to get x cubed there. What are the coefficients of these x's? They're all 1s. So it'll be 1 times 1 times 1. 1 times 1 times 1 is going to be a positive 1. So it will be a positive lead coefficient. So it's kind of nice. Without having to do a whole lot of work, right, just kind of like looking at the problem, we can figure out what the end behavior is going to be. Okay? Since it's odd and positive, that means it's going to look like x cubed. Something kind of like this behavior for our end behavior. So in other words, and here's the end behavior written right here, as x approaches infinity, f of x will approach infinity, right? You can see it right here. As x goes to infinity, it's going to go to infinity. As x goes to negative infinity, as we go further left, we're going to go down. So x approaches negative infinity. So there's our end behavior. Okay? So we can tell that without actually having to graph the polynomial. We can just look at it and see. Okay? All right? Some other things we need to identify. We also want to we want to figure out the x-intercepts. Okay, or you can say the zeros or the roots, whatever you want to call them. Okay. Looking at our polynomial here. Okay. Looking at our polynomial here. That's funny. What are our zeros going to be?
Wait.
What will the zeros of this polynomial be? When will this thing equal 0? Here, I'll write it up here so I can show you can see what I'm talking about. For what x values will this thing equal 0? So you have these three things that are multiplying, and they are going to equal 0. If they're multiplying to make 0, we can use the zero product property here. We can say that x is 0. We can say that x plus 2 is 0. We can say that x minus 3 equals 0. So one of our zeros... Yeah, we want to solve. So x is negative 2, and x is positive 3. That's right. Those are our three zeros for our polynomial. Very easy, right? It's nice that it's factored out there for us, because we can just then, there they are. Okay? And so if we kind of like look down here at the bottom of the page, you'll see, here's the answer. Well, there's the 0 at 0. There's the 0 at negative 2. There's the 0 at 3, right? You can see those points. There's one right there. There's the other 0. There's the other 0. There's all three zeros. You can also see the end behavior, right? As x approaches infinity, f of x goes to infinity. As x approaches negative infinity, f of x will approach negative infinity. So it's only a matter then of figuring out what happens between. What happens between? Okay? And so I like to call this the middle behavior. Okay? So figure out that middle behavior. Okay, to see that it does in fact it goes up and then it goes down here between these things. We're going to look at this is what I like to call it the middle behavior. We're going to take those zeros and put them in numeric order, so negative 2, then 0, and then 3, and that creates some intervals here for us. Okay. What's the number between negative 2 and 0?
1.
Yeah, let's pick negative 1. And what's the number between 0 and 3? 2 or 1, let's just pick 2. Okay? We're going to test these numbers back into our polynomial here. We're going to plug them back in. Okay? So I'm going to do f of negative 1, which is going to be equal to negative 1 times negative 1 plus 2 times negative 1 minus 3. And then the other thing I'll plug in 2, and I'll say 2 times 2 plus 2 times 2 minus 3. Okay, so I just plug those in. There, like that. And I just do a little simple math, right? Okay, so we have the negative 1 there. Negative 1 plus 2 is 1. Negative 1 minus 3 is negative 4. 2 is 2. 2 plus 2 is 4. 2 minus 3 is negative 1. So I multiply this all out. Negative 1 times negative 4 is positive 4. 2 times 4 times negative 1, negative 8. So what does this tell me? That I have the point negative 1, 4 on my graph, and I also have the point 2, negative 8 on my graph. Okay, and if you look here, negative 1, there's negative 1, and then 4. Now you'll notice there's no scale on the y-axis here. And these kind of sketches, we're not worried too much about the precise height of our polynomial, so we just know that since it's negative 1, 4, it's going to be positive, so it's going to be up here somewhere. Likewise, here with the 2, it's going to be negative 8, so we know it has to go down somewhere. That's all. So it's just going to go. So we got to, we put a little point here, put a little point here, and just go up, down, up like that, and connect those dots. And voila, we have our graph. Okay? So that is our ultimate goal here. Let's try another one, though, and see what we can do. Because this one was already kind of worked out for us. There was a lot going on and stuff. So let's try another one here. Let's take a look at letter B. But I'm not going to do any work up here. This is like, it's too busy. I don't like all these blanks. We're just going to do it down here. So if you'll permit me, I'm going to rewrite it. F of x equals negative x minus 4 times x minus 1 times x plus 1 times x plus 2. Okay? I actually just got done teaching this very same thing in my pre-calculus class. So you guys are doing stuff that I just did in pre-calculus too. So I don't know if it makes you feel any better or worse or whatever. Maybe you don't care, but it is kind of interesting. We just did this in pre-calculus. Okay? All right, so let's go through things again here. Let's do the end behavior first. So to determine that end behavior, we need to find the degree, and we need to find the lead coefficient. Okay, so let's go to someone who's here. Katie! So Katie, what will the degree of this polynomial end up being? If we were to multiply it all out, what will be the highest powered term that we have there? X to the 4th. So that means we have an even degree. Remember, even degree polynomials, their end behavior either both goes up or both goes down. Okay? So that's why we need to figure out this lead coefficient. Katie, what would the lead coefficient be here? Well, so you found the degree by taking this x times this x times this x times this x, right? X to the 4th. Same idea as the lead coefficient. What's the lead coefficient of the x here? A 1. And what's the lead here? 1, 1, 1, right? So it's 1 times 1 times 1 times 1. So it's, but there's a negative in front of the whole thing. So it's going to end up being a negative 1, which is negative. Okay. So our end behavior then, as x approaches infinity, f of x will approach what? Anybody? Ooh, careful. It's an even degree, but since it's a negative lead coefficient, it's going to look like that. So it'll be negative infinity. And as x approaches negative infinity, what will f of x approach? Negative infinity as well. Yeah, they're both going to go to negative infinity because of that negative lead coefficient there. Okay, great. So there's our end behavior. What about our zeros? So in other words, we'll do 0 equals negative x minus 4, x minus 1, x plus 1, x plus 2. Okay. So I got to zoom in some more on that. That's like kind of small. Okay. So Patrick, what will our zeros be here? Can you tell what the zeros are going to be just by looking at them here? Mm-hmm. Yes! Do you know why it's 4? No. Okay. You want to help him out?
Yeah.
How'd you know?
Because it's 4x.
No, that's not. You're right though. 4 is, that's 4. 4 was right though, but not for that reason. Not for that reason. Right. So all 4 of these things, right? They're multiplying. All 4 things here are multiplying to equal 0. We can use the zero product property. So that means each one of these things can equal 0, and so that's where you should get the 4 from, because you have x minus. That's what you meant to say, right? That's what you meant to say. Yeah. I'm sorry. All the pressure. I put too much pressure on you. Yeah. Okay, so you said each one of these factors equal to 0, and we get then x equals 4. We get x equals negative 1. We get x equals 1, and we get x equals negative 2. Is that clear, Patrick, now? Is that a little more clear? Yeah. Okay. And since we have those zeros, we can go ahead and plot those zeros right up here on our little grid, because we're going to be plotting them. So let's go ahead and plot 4, negative 1, 1, and negative 2. Okay? We can also go ahead and plot our end behavior as well. Okay? So as x goes to infinity, that means the farthest right point here, so there's our farthest right point, f of x should go to negative infinity. So I know my farthest right point, if I go further right, I should be going down. Okay? Similarly, as x approaches negative infinity, as I go my furthest left point, f of x should also be going down. And so now I have to figure out the middle behavior. What happens between all of these zeros? Okay, well you guys can probably guess, right? So like after negative 2, what do you think is going to happen? Should I go up or should I go down from the negative 2? Up, and then I got to hit a peak and then go back down through it. And I'm going to probably hit the valley down here and then back up through here. And then up and up and up and then back down through there. Something like that, right? That's what it probably looks like it's going to happen here. But let's just check to make sure. So again, put your zeros in, or you just pick numbers between these intervals here. So, ooh, okay, this is going to be not so fun because you have to pick a fraction here, but that's okay. So again, between, I guess I'll squeeze this in here. Middle behavior, we'll say. All right, let's see. I got to put these in order. So negative 2, then negative 1, then 1, then 4. So we have to pick numbers in each one of these three intervals here. So what's the number between negative 2 and negative 1?
Negative 0.5.
Negative
1.5.
Negative 1.5. There we go. Okay, how about a number between negative 1 and 1?
0.
0. And how about between 1 and 4?
2.
2. Sure. Okay. And they're going to plug each one of these back into our function. So I'm just going to say f of negative 1.5, and then I'll say f of 0, and then I'll say f of 2 here. Okay. Now, I didn't leave myself very much space, so I hope I can squeeze this all in, but I'm a little doubtful. Okay. Let me show you a little trick we can do here, and then I'll kind of just shortcut it and use the calculator for the rest of these. Let's say, for example, that I want to see what happens when I plug in f of 2. When I plug in f of 2 back into my function, and you can use this one, I guess we'll plug my f of 2 back in the function here. I'm going to have a negative, and I'm going to have 2 minus 4. But what's 2 minus 4? Two minus 4. Negative 2. So I'm going to say it's negative, right? Okay. What's 2 minus 1? It's a 2 minus 1 is positive 1. So it's a positive number. 2 plus 1 will be positive as well. 2 plus 2 will be positive as well. Okay. Notice here I'm not so concerned about what the number value is. I'm just concerned about the sign, whether it's positive or negative. Now, if I have a negative, and I multiply by a negative, what is it now? Positive, and then I multiply by a positive, and a positive. What is it? Positive. So at the 2, I need to be positive. Okay, so from, between the zeros here of 1 and 4, I need to be positive. So there I just drew it positive. I drew the graph positive. Sorry, you can't see it. There it is. All right. Between the 2 and the 4, the 1 and the 4 there, I drew the graph positive. Okay. Let's try with a 0. We can do the same thing. Okay, there's a negative there. What's 0 minus 4? It'll be negative, negative 4. 0 minus 1? Negative. 0 plus 1? Positive. 0 plus 2? Positive. So now we have a negative times a negative times a negative. So what's a negative times a negative? But then times a negative, negative. So these three things multiply to make a negative, and it's times a positive times a positive. So it'll be negative. Okay? And so at 0, we expect to be negative, so somewhere down here. So we can just we have the negative part of our graph right in there. Okay? Now let's check negative 1.5. Again, we're not so much worried about the value, just the sign. So we're going to have the negative that's in front, times, what's negative 1.5 minus 4? Well, will it be positive or negative? It's going to be negative. Negative 1.5 minus 1? It's going to be negative. Negative 1.5 plus 1? it'll be negative. And then finally, negative 1.5 plus 2, positive. Okay, so a negative times a negative, positive times a negative, times a positive, or times another negative, sorry. It's positive, so times a positive, positive. So negative, 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 positive, it becomes positive. And so we just then go positive between those two pieces, and there's our sketch. Bless you.
Bless you.
Okay? Now, if you don't believe me, you're like, Mr. Meyer, this is like black magic witchcraft right here. There's no way this works. Let me show you. Type this in my calculator. We're doing some mathemagic here. Bless you. Okay, if we graph this thing, okay, you can see the graph right here. Now, granted, is it to the same vertical scale, right? Is the stretch of the scale the same? No, but you still have the basic shape, right? It goes up, peaks and goes back down, and then goes back up through the 1 there, back up through the 1, and then peaks up here, and then back down through the x-axis. Okay? There's actually no way that I know of at least, for us to find these precise maximum and minimum and maximum values without using calculus. Okay, so that's why we're just estimating these things. There's no precise way for us to do this without using calculus, and so that's why we're just kind of estimating these things. Okay, shall we try one more here? Or do you guys think you got it? Do you want to see one more? One more? AJ's one more. All right. We'll do one more. This one won't be as long because there's not nearly as much stuff here. All right, and then I'll give you guys your assignment. Okay, so we'll be done after this one way or the other. I mean, done, and then you guys will get your homework and stuff like that. Okay, but I won't give you a whole lot of these too because these take some time. All right, so again, we have 3 things you got to find. We got to discover the M behavior. We got to find the zeros, and then we want to talk about the middle behavior, and then we'll graph. Okay, so really, I guess 4 steps. Okay, for the M behavior, we need to find the degree and the lead coefficient. Okay, M behavior M behavior requires degree and lead coefficient. So, Jordan, what do you say here? What will the degree of this polynomial be? What's the highest powered term going to be here? So, x to the 2 is the highest one we see here, but remember, this x squared is going to get multiplied with this x, which will end up being x to the 3rd. So the degree is 3, which is an odd degree, meaning they're going to disagree, right? It's like an I'm a little teapot kind of situation. We're going to go, one's going to go down, one's going to go up, or one's going to go up and one's going to go down, you know, kind of thing. That's right. Who knew when you were doing the little I'm a little teapot dance, you were learning about M behavior? Okay, probably not, but you know, hey, it kind of fits. Anyway, what's the lead coefficient here going to be, Jordan? Very good. We have a -1 here with this x squared. We have a +1 here with this x, so it'll be -1. Yes. Yes, you may. So just like we determine the degree by multiplying, like imaginarily multiplying these two things together, we're going to do the same thing to get that lead coefficient. It'll be -1 times a +1 there, so it's just going to be -1. So in other words, it's negative. Okay? So since it's negative, that means as we go out to the right, we're going to go down. And as we go out to the left, we're going to go up. Right? This is like a cubic, but like a flipped cubic. Okay? It's going to look something like this. So we'll say, as x approaches infinity, f of x is going to approach what? -infinity. Very good. And as x approaches -infinity, f of x will approach what? +infinity. That's right. So there's our M behavior. Okay, there's our M behavior. Again, the odd degree means we're going to have different N behaviors. One's going to go to +infinity, one's going to go to -infinity. Since it's a -1 lead coefficient, it's going to be this like reflected cubic kind of thing. Okay. All right, let's find some zeros. So we'll take this thing and have it equal to 0. Okay. Oh, David just left. Let's go to Eve. So Eve, how do we find the zeros? We have this thing times this thing equals 0, so what can we do now to find the zeros? Or what will our zeros be? You can even tell me that. Okay, so we have two things here that are multiplying to make 0. Do you remember that zero product property? Does that ring a bell, right? If two things multiply to make 0, what must be true about one of these two things? Not positive. Nope. Yeah, if two numbers multiply and they give you an answer of 0, if you have two mysterious numbers, right, and you're multiplying it and your answer is 0, that means one of those two numbers has to be 0. There's no other way to multiply to get 0 without a 0. Exactly. So that means either x squared equals 0 or x minus 4 equals 0. Or sorry, I should say negative x squared equals 0. So then to solve this little equation here, E, what will we do? Yeah, so it's x is 4. That's one of our zeros. Okay? Don't think too hard about it. You're making it harder than you need to. So we have a negative 1. Let's divide both sides by negative 1. Okay? But what's 0 divided by negative 1? Oh, 0. Right. And then what's the square root of 0? Again, don't think too hard about this one. It's 0. Very good. Yes. So we have a 0 at 0 and a 0 at 4. Yep. So we're going to, over here, we can go ahead and plot those points right away. So put our 0 at 0, put our 0 at positive 4. Okay. And then we want to discuss the middle behavior. So now if you look here, there's only 2 zeros, so we only have to pick one point. So pick a point here between any, yeah, so 2. 2 is right in the middle. That'll be nice. So let's do f of 2. Okay, actually, let me do it this way. So again, I like to put my zeros in order, and then we'll pick the 2, and then we'll do f of 2. Okay, so now let's again think about this here. It's going to be negative 2 squared times 2 minus 4. Okay, so let's think here. 2 squared 4, but it's going to be a negative 4. 2 minus 4, negative 2. But we multiply them, so it ends up being 8. You added. Okay? So at 2, it's going to be roughly 8. So at 2, we're going to be up here. So we know from here to here, we're going to go like this. Okay, something like this. So now we're not quite done, though. We've got to include that end behavior as well, right? So let's see here. It says here, as x approaches infinity, f of x is going to approach negative infinity. So as we go far to the right, we're going to go down. So let's go to our farthest right point and go down. Well, that makes sense. There it is. Okay, this next one's going to be, this next piece is going to be a little bit funky, though, so just hang on here. As we go farther to the left, what's our function got to do? Go up. What? Our farthest left point is 0. It looks like it should go down through that 0, but it doesn't. We're supposed to do this. Like that, yes. What a silly function indeed. Okay. Yep, it just comes down, touches the 0, and then goes right back up. Okay? Now, that's a different kind of behavior than what we experienced at all the other zeros we saw, right? If we go back, okay, to the previous page, here were our 3 zeros, and the graph went through the 0 up, through the 0 down, through the 0 up. If we go to the previous, or the next one after that, there were our 4 zeros, and went up to the 0, down to the 0, up to the 0, down to the 0. But then here, it comes down, touches the 0, goes up, and then goes through that 0. What's unique about this? Miranda, what do you say? It's got the negative in front of it? Well, but we've had a negative lead coefficient. Let me see here. I think, yeah, the one prior to this. Letter B, right, this guy right here, this one had a negative in front of it as well. So they both have a negatives, but that didn't affect it. What's different about this polynomial, though, that the other polynomials don't have? Yes, it's got a square there. And notice, what's the 0 that we got from this x squared? The 0, right? The 0 that we got from the x squared was the 0 at 0. And notice that's the 0 that had that weird behavior. So there is a link between the fact that this is x squared and that we just come down and touch this thing. This is called a double root, right? Technically, there's like a 0. The 0 is kind of like a double root. It happens twice, essentially. And so you don't go through the 0. You just come down, touch it, and then go right back up. So if you see a square in your, when you're sketching your polynomial functions, that's what's you're going to notice that kind of behavior. Okay? So let's get you guys an opportunity here to excuse me, try these. So let's see. I would like you guys to try numbers 9 and 10 on page 259. Okay, 9 and 10. I'll just have you do 2 because these do take some time. Okay, so 9 and 10 on page 259. Mr. Widmeyer. Ooh, and I'm also going to have you guys try 14 on page 261 as well. So 9, 10, 14. 9, 10, 14. All right, 9, 10, 14 on page 259. Give it a shot here. I'm going to stop.